Okay, so last time we were talking about these partial derivatives and the interpretation. These were the tangent line or the slope of the tangent line in a particular direction, either the x direction, the y direction, or if we have functions of even more variables, we can say the z direction, and so on and so on. And we learned about higher derivatives. We also learned about when we can swap the order at which we differentiate with respect to these variables, as long as their derivatives are continuous. So today we're going to pick up with continuity versus differentiable. So when is a function continuous? When is it differentiable? Let's kind of dive in. With functions of one variable, there was no possible way for a function to be differentiable at some point x naught without being continuous at that same point. Right? So if the derivative existed, that meant the limit from the left and the right of x naught existed for this the differentiation limit, right? So that implies that the function is certainly continuous at that location. So if we have differentiability, it implied continuity. Okay. So consider now the function of x and y that is piecewise defined as 0 everywhere that the product of x and y is not equal to 0. And it's 1 everywhere where the product x times y is equal to 0. So this just means anywhere that x times y is equal to 0, we get this 1. So if we have x being 0 or y being 0, we're going to put a 1 there. And everywhere else, it's going to be 0. So you can think along x equals 0 or y equals 0, we just have the value of 1. Everywhere else, we have the 0 value. This function is 1 along the x and y axis. But 0 everywhere else. The limit as x, y goes to the origin of our function f of x, y does not exist because we get two different results, right? If we're traveling along the X or Y axis, we'll get a value of 1. But if we travel anywhere else, we're approaching 0, right? So the limit obviously doesn't exist here. Notice that if I wanted to know the x derivative of my function at 0, 0, I can write that as the limit as h goes to 0 of f at 0 plus h 0 minus f at 0, 0 all over h. This is the limit as h goes to 0 along the trace in the x direction, and we called that g before. So let's kind of write in the side margin here that g of x is equal to f of x 0. But g of x, which is our sorry, it's actually not the, it's not the partial. It's just a function at x 0. Along this trace, y is equal to 0. So this is just 1. This limit exists. The x derivative doesn't see the discontinuity because along that trace, it's equal to 1. Now, if we slightly increment it and we're not right on the origin, of course, we're going to have problems because the limit's not going to exist. But we can also think about it in the y direction as well. If we took f partial y at 0, 0, along that same direction, we have the function as the constant 1. It doesn't see the discontinuity, so the limit exists. So even though these derivatives at this location exist, the function is certainly not continuous at the origin because limits from any single direction don't provide the same thing. So that's kind of the fundamental difference between differentiality and this continuity, is because derivatives here, these partial derivatives, have particular directions, but continuity implies that the limit approaching from any direction is the same. So if the partial derivatives fx and fy of a function are continuous, throughout an open region, we'll talk about what that means, that we'll call R, then f is differentiable at every point of R. So we have to be a little bit more strict when we define when something is differentiable. Because obviously in this case, this example, the derivatives existed in the x and y direction, right? But the function is not continuous there. So something's going on, right? So we have to be a little bit stricter when we're talking about it being differentiable. So the derivatives in particular directions might exist, but you can imagine, and we'll talk about this later, about derivatives in an arbitrary direction. Certainly those shouldn't exist in this example, right? Because that limit wouldn't exist, right? You're going from 0 and then all of a sudden you spike up to 1. It can't happen. So what we have to do is define differentiability as a small neighborhood around our point. So consider the origin in our example here. It's certainly not differentiable, or the derivatives aren't continuous functions around the origin, not just at the origin, but around the origin. You can think of just a very small circle, right? And it has to be a finite circle. It can't be just the point. It has to be, and you can make it as small as you want. You can keep on thinking infinitely small, but it still has to be a finite neighborhood around that origin, right? And that finite neighborhood around that origin has problems with continuity, right? So thus we say that it's not differentiable because it doesn't now have continuous first derivatives in our neighborhood around our point rather than just at the point itself, because now we have to talk about approaching from any direction. Okay, so that brings us to a theorem. If a function f of x and y is differentiable at some point, now using the definition that we've defined for differentiable, then f is continuous. At that point, right? And that follows our logic with functions of one variable, right? If it was differentiable, it was certainly continuous. But now with our stricter definition of differentiable, we can make the same claim again for functions of more than one variable. If our function is differentiable using the stricter definition, then it's continuous at that point as well. So now we have to talk about this small neighborhood around that point for differentiability. Okay. So we're not going to talk much about differential equations because that's a whole class on its own. But what we are going to touch on is just a tad of partial differential equations. And we're certainly not going to learn how to solve them. In Calc 2, you learned what a differential equation was, and in Diff-EQ, you'll learn how to do more advanced solutions of those. And together, Calc 3 and Diff-EQ make partial differential equations, which are even harder to solve. But we're going to just talk about them in general. So in Calc 2, we looked at ordinary differential equations. And what that meant was we had ordinary derivatives in them. Oh, I don't know why it has an extra I. So an ordinary differential equation, or an ODE, might look like I have some function y of x, and its derivative is equal to itself. Now, the whole point of differential equations is you have a relationship like this where you have differentials, right? So I have a differential equation here. And the goal is to find y of x, right? And you can kind of think this is probably a really easy differential equation. If you think about it, what do you know that has, what function has the property that its derivative is equal to itself? Well, that's just e to the x, right? But you talk about that in diffie-q. But so the goal is to find y of x. Now, there are a bunch of physical laws in our world that are described by partial differential equations, because the world that we live in isn't just one-dimensional, right? It has 3 spatial and 1 temporal dimension. So these talk about these partial differential equations when we have partial derivatives in them as well. One such example is the Laplace equation. And the Laplace equation is written as the second derivative of some function of x and y. And I'm taking 2 partial x derivatives, and then I add the second partial of y derivative to this, and I should get 0. So the goal is to find this u that satisfies this expression. We're not going to talk about how we do that, but we're going to see if something is a solution. So all we're going to do is just plug it in, see if it works. So this has a lot to do with like heat conduction, fluid flow, electric potentials. Solutions to this are called harmonic functions. And they show up in math all over the place. But notice that there's no time derivative in this, right? Nothing. So this is kind of like a static expression, right? It holds for all time. Well, let's talk about the wave equation. So the wave equation will kind of detail, oh, I'm playing my guitar and I pluck a string. How does the vibrations of that string propagate through time? Well, this is written as the second derivative of a function u. So we're taking 2 time derivatives, and it's equal to the wave speed squared times the second derivative with respect to x. So this kind of details how simple waves kind of propagate, right? And of course, adding more terms makes it a better model for different things. There are so many PDEs, or partial differential equations, that describe how the world works that people study, and they're not easily solved. Sometimes you have to use numerics. You have to use a computer to kind of figure out what's going on here, because the analytic solutions are just escapable, right? No one might know what they are. Okay, so let's do an example. So we're going to prove that f of xy equal to the natural log of the square root of x squared plus y squared is a solution to the Laplace equation. So we're not asked to solve the Laplace equation. We're just given this thing and we're double checking to see if it is a solution. So that means, does it satisfy the PDE? Can I plug this in? So f is a solution if its second x derivative plus its second y derivative is equal to 0. So what I'll do is I'll just calculate those derivatives and see if they end up canceling. So the first thing I'm going to do is take the first x derivative. So because we're in this natural log, we'll have a 1 over what's inside, or the square root of x squared plus y squared. Then I have to multiply it by the derivative of what's inside, which gives me a 1/2 x squared plus y squared to the negative 1/2. And then I have to differentiate what's inside the square root, which gives me a 2x. So I can simplify this, and this ends up just being x over x squared plus y squared. So now the second derivative with respect to x, I have to do a quotient rule. So I have 1 over the denominator squared times an x squared plus y squared times 1 minus x times 2x. So low d high minus high d low. And I can simplify this a little bit, and I can get y squared minus x squared all over x squared plus y squared squared. So now you can imagine that these y derivatives are going to be fairly similar. So the first y derivative ends up giving me y over x squared plus y squared. And the second y derivative ends up giving me an x squared minus a y squared all over x squared plus y squared squared. So you can probably already see it when I add these two second derivatives together. They have the common factor of x squared plus y squared squared, but one has a y squared minus x squared, and the other one has an x squared minus a y squared, which ends up just being 0. Pretty cool. For all x and y, both of the second derivatives added together equals 0. So this is a harmonic function. This is a solution to the Laplace equation. PDEs are really cool. I really hope that you go on to study them. They describe our world. But for now, that's pretty much all we have to say about it. You might see a homework problem here or there on it, just to see if something is a solution, but not actually solving a PDE or a partial differential equation. Okay, so we're going to move on to the next section, which is 11.4. This is tangent planes and linear approximations. So if we consider the surface z equals f of x and y, where f has continuous first order partial derivatives, where f has continuous first order, that just means first derivatives, partial derivatives, if we look at the traces when x is equal to x naught and y is equal to y naught, we create two curves that intersect at the point x naught, y naught. The tangent line along the y equals y naught trace at x naught, and the tangent line along the x equals x naught trace at y naught create a tangent plane. To the surface at x naught, y naught. So let's just kind of quickly sketch what this is saying here. So maybe again, we're looking down at our surface. We can't really see the elevation of it, but we just want to see direction here. So I'm taking a trace in both the x and the y direction here. So maybe close to where they intersect, my function kind of looks like this in this direction, and then maybe like that. No, it's kind of hard to do it like this. Maybe it looks something like that in this direction. In the x direction, I have a tangent line. In the y direction, I have a tangent line. And in those create all we need to create this tangent plane to the surface at that point. Okay, so how do we find this plane? We know the form of a plane is a x minus x naught plus b y minus y naught plus c of z minus z naught equals 0. So now what we're going to try to do is solve for this z minus z naught. So we're going to divide by c. So we're going to let lowercase a be negative a over c, and lowercase b be this negative capital B over c. And we can rearrange this and we can say that z minus z naught is equal to some constant times x minus x naught plus b of y minus y naught. So now the goal is to find out what this a and b are. And this will give us the equation of our tangent plane, right? And then you can kind of draw a lot of similarities with the tangent line for functions of one variable. So to find a and b, what we're going to do is we're going to first notice the trace of this when y is equal to y naught. So if y is equal to y naught, I get that z minus z naught is equal to a x minus x naught. So this is what the tangent plane looks like along the trace y is equal to y naught, right? But then we know that that should be the tangent line of the function at the point x naught, y naught along that trace. So to be tangent, we need the slope a to be the x derivative at x naught and y naught. You can do the same logic, so just repeat it along the trace where x is equal to x naught, and we know that the b has to be the y partial derivative at that point. So we repeat along the y equals y naught trace. And we get that b is the y partial derivative at y naught. So then we can write down this whole expression for planes, for tangent planes. That is, if we have an f and it has continuous partial derivatives, an equation of the tangent plane to the surface z is equal to f of x and y at the point x naught, y naught is z minus z naught is equal to f of sub x, x naught, y naught times x minus x naught plus our partial y derivative at x naught, y naught, and y minus y naught. Oh, yeah, sorry, I missed that question. Yeah, this is supposed to be along the x equals x naught trace. Thank you. So this is our expression for a tangent plane. And it doesn't really look that far off from the equation for a tangent line, right? In fact, it just has an extra term, an extra linear term, in fact. So you can kind of imagine that if we go up in dimension, you can kind of think of the tangent plane or whatever, the hyperplane, whatever have you in higher dimensions, is going to follow this same logic where we're just going to tack on these additional terms, where in that corresponding direction, we have a coefficient that is determined by the first derivative in that direction. Okay, so let's do an example. Let's find a tangent plane. So we have our function, which is x squared minus x times y plus 1/2 y squared plus 3. And we're trying to find it at x is equal to 3, y is equal to 2. Okay. So the three things we need are z naught, which is our function at x naught, y naught. We also need the partial x derivative at our point, as well as our y partial derivative at our point. So let's go ahead and calculate those things. So sorry, z naught is 3 squared, so we're just plugging in our x and y here, minus 3 times 2 plus 1/2 2 squared plus 3. This ends up giving us 8. So first we look at the partial derivative with respect to x. We're just going to get a 2x minus y. So then at this point, 3, 2, we just get 4. The y partial derivative will just give us a negative x plus y. So this is, and we're going to evaluate at 3, 2, and we'll just get a negative 1. So the tangent plane at 3, 2 is then z minus 8 is equal to 4 times x minus 3. We have a negative 1, so do minus 1 times y minus 2. And you can simplify that a little bit, but that is our tangent plane. So not too hard. All we really need to do is find the z naught, fx, and fy. So one question that you might have is, why do we even really think about this tangent plane? Well, remember the first thing you did when you learned about these tangent lines was to use it as an approximation of the function, close to the evaluation point. So if you had x naught and y naught, maybe you moved some epsilon away from that, and then you wanted to know a good approximation of the function there. So we can use these linear planes, these tangent planes, to kind of help us with that. So these are linear approximations. So recall from R2, we use the tangent line to approximate the function by this linearization. Y minus y naught is equal to the derivative at x naught, x minus x naught. So that was our linearization from Calc 1. We have a question. Don't we have to simplify the plane equation further? You can, but that's still the plane equation. Yeah, so we could simplify it, and we should. But we're gonna talk about some more important stuff here. So recall from R2, we're talking about this linearization. In R3, we can use the tangent plane to kind of approximate around the point x naught, y naught. So if we start with the tangent plane, at x naught, y naught in R3. Yes, not simplifying the plane equation will lose you points on the test. Yeah, all right, we're gonna go simplify it. This is, all right, so we have z is equal to 4x, and then I'll have a minus 12 here, and then I'll have a plus 2 here, so I'll have a minus 10, and then I'm adding over this 8, so this should just be a minus 2. Okay. Where was I? Oh, so we're starting with the tangent plane at this point. So we have z minus our z naught, which is f at x naught, y naught, is equal to f of x sub x at our point x naught, y naught, x minus x naught, plus f sub y at x naught, y naught, times y minus y naught. So if we kind of think about this as an approach, because this is the equation for the tangent plane, not the function. But what we can do is say that f of x and y is approximately the linearization of our function, which we call this L of x and y. And this is equal to f at x naught, y naught, plus f sub x at x naught, y naught, x minus x naught, plus f sub y at x naught, y naught, times x minus, y minus y naught. So basically all we're doing is just following the tangent plane at some point. So maybe our tangent plane is pretty close to our the point of interest, but we know what the tangent plane is, so we can plug in these points. And the closer we are to x naught, the better of an approximation this is going to be. Right? So maybe our function's really hard to deal with, and we don't want, it's hard to plug in points. But once we know the tangent plane, maybe it's easy to plug in points, and it's a good approximation to it. So where L is the linearization of f at x naught, y naught. So it is a function of x and y, because here they are, and they show up in here. But it takes the form of the tangent planes of the function f at x naught, y naught. So from here, let's talk about differentials. Actually, why don't we take our 5-minute break here, because I think we're a little bit over. Yeah, so we'll pick up in about 5 minutes. So go use the restroom, get a drink of water, and we'll be right back. Okay. So let's talk about differentials. for a function of one variable, we said that y was equal to f of x. We defined that dy over dx was f prime of x, right? Just two different ways of writing the derivative, but let's kind of dig a little bit deeper here on this left. I have some infinitesimally small change in y over a similarly small change in x, right? And we called this the first derivative over function. Now, of course, this had to be when our function f was differentiable. So instead, we could write that the small change in y is the first derivative times some small change in x, right? This is like the change in y is this tangent slope times the small change in x, right? And that's completely justified. So we can kind of think about this as not the limit, but we can use this as an approximation. Kind of this is what, you know, we were doing before with linearization here. So this is much like describing how the change in y is related to the change in x. We call delta y the increment and dy the differential. So the difference is that the change in y, this delta y, is a finite difference, whereas the differential dy is some infinitesimally small change in y. So now we're in R3. The differential dz relates to how the slopes of the tangent plane changes with dx and dy. So we can say that dz is equal to f partial x at xy dx plus f partial y at xy dy. Or this is partial f partial x dx plus partial f partial y dy. So it's worth noting that these do not cancel because this is a partial x and this is a dx. We say that dz here is then the total differential. So you might hear me say when I'm talking about what you consider like a normal derivative instead of a partial derivative, I'll call that the total derivative, right? So here we have this dz instead of a partial z. So we call that the total differential. Okay, so let's do an example where this might be useful. Like, why would we ever want to consider this type of like approximation? Well, let's consider a tank with volume that's equal to pi r squared times h. So it looks like kind of like a standard cylindrical tank. So the question is, how does the volume change with small changes to R and H? So our dV, our volume here, the change in the volume will be related by these partial derivatives. We have to take partial V, partial R times dr plus partial V, partial H of dH. So we can actually do those partial derivatives. This is 2 pi r times h times dr plus pi r squared dh. So this kind of tells us how the change in volume is going. So if I have some small change in R, I plug in my existing R and H, and I have some small change in height, and I plug in my existing value for R, and I'll get some change in the volume. So imagine if the tank started with R being 5 feet and H is 25 feet. If I plug those in, I get dV is 250 pi times dr plus 25 pi times dH. So you might see what is more impactful for the volume if I already have a radius of 5 and a height of 25. Right? It seems like if I changed the radius by some small amount, it would be much more impactful than doing a small change in height at this point. So let's continue this logic. So what if we change R by 0.03 and H by negative 0.1. So my change in volume would be approximately 250 pi times 0.03 plus a 25 pi times a negative 0.1. This comes out to being around 15.7080 feet cubed. So even though I subtracted some height from this and added a very small amount to the radius, I still actually gained volume. Another question might be, what percent change is this? Well, I'll have my dV over my existing volume. So this is about 15.7080 divided by V. If I plug in R is equal to 5 and H is equal to 25. Or this comes out to being roughly 0.008. So the percent change is 100 times our quantity dV over V, which in this case is 0.8%. So by subtracting just a little bit of height and adding an even smaller amount to the radius, I increase my total volume by 0.8%. Okay, and that's it for 11.4. That's a pretty short section, just talking about these approximations in the linear case. Okay, I'll give you just a second to kind of write that down if you need to, and then we'll go to another page. Okay, so let's start section 11.5. Oh, we have a question. Let's go back. Why didn't we change the radius and height in the original volume equation? I'm not sure when we're talking about percent change. because this is the original volume and we want to know how much we've changed from the original volume. Is that your question? Yeah, so yeah, we have, if our percent change, we have to use the original volume. Okay. So 11.5 is the chain rule. This is an important section. This comes up. So recall for functions of one variable, when y is equal to f of x and x is equal to a function g of t, that if I wanted to take d dt of y, this was d dt of f of x, which in turn is d dt of f with the function g of t inside of it. And this is how we learned how to do the chain rule in Calc 1. This is f prime with the original g of t in the inside times g prime of t times dt dt. And that's just going to be 1. So we're left with f prime. And now g of t, remember, is x. And then we have g prime of t here. Or we can write it as dy dx times dx dt. Right, and that makes sense. If you look at this, this was in fact right here dy dt. Right, and more or less you can kind of think about these total differentials just canceling here. So we have this dx and this dx here, and then we get dy dt. So now, if we have that z is equal to a function of x and y, where x is equal to a function of t, y is equal to a function of t, what is dz dt? So first off, does this even make sense? Can we take this total derivative of z? Well, if you think about it, if you plug in x and y as their functions of g of t and h of t, f is only defined as a function of t. So it is just a function of one variable. So it makes sense for us to take this total derivative rather than a partial derivative. So let's start with differentials. The change in z was from just before we said partial f, partial x, the change in x plus partial f, partial y, the change in y. So from this, we can say, if we divide both sides by a change in time, or change in t, so we divide by change in t, this is approximately partial f, partial x, change in x over change in t, plus partial f, partial y, change in y, and the change over the change in t. Now this is just approximate using differentials, but in the limit, I have dz dt, so the limit as the change in time goes to 0 of my change in z over my change in t, I get partial f partial x dx dt plus partial f partial y dy dt. And because we know that x is equal to just this function f, we can just write this as partial z partial x dx dt plus partial z partial y dy dt. And that's how we do this chain rule for functions of more than one variable. In fact, just for two. So we had that x and y were both corresponding functions of t. So rather than the product rule looking like this for functions of one variable, for two, we have two sets of products. And that continues in general. So if we're in where we have three variables, we'll have a third set of another product. So this is the chain rule case one. So let's do an example. We're going to find dw dt when w is equal to x times y, where x is equal to cosine of t and y is equal to sine of t. Okay. Well, according to the chain rule, dw dt is equal to partial w partial x dx dt plus partial w partial y dy dt. So these are the four things that we need to compute. We have that partial w partial x is equal to y. We have that partial w partial y is equal to x. We have that dx dt is equal to negative sine of t. And then we have that dy dt is cosine of t. Now, notice that we have our partial w partial x and partial w partial y in terms of y and x still. We'll have to convert those into their corresponding functions in time. So y was equal to sine of t, and x is equal to cosine of t. So now we can plug those all in. dw dt is equal to sine of t times negative sine of t plus cosine of t times cosine of t, where this is cosine squared of t minus sine squared of t. There's a nifty little trig identity for this. This is just equal to cosine of 2t. Okay. So you might be thinking, why did I go through all this trouble if I could have just plugged in what the representation of x was into my function w, right? So w is equal to x times y. So couldn't that just be cosine of t times sine of t? You're right. You could definitely do that. In fact, let's do that now. Does this actually work out? Well, w is equal to x times y, which is equal to cosine of t sine of t. And another nifty little trig identity is that this is 1/2 sine of 2t. So dw dt would be equal to d dt of 1/2 sine of 2t is equal to cosine of 2t. It works. So you might be asking yourself, why are we doing this? Why would I just want to plug in the functions that represent x and y originally and just do it that way? Sometimes this is a really easy example. So you can imagine that cosine and sine into a product just of x times y, maybe it's a lot easier to just plug those in and then take that time derivative. In other cases, maybe plugging those things in and taking one derivative is very, very hard in comparison with just doing these partial derivatives and these easy total derivatives here. And we need to actually form the groundwork for when we do the case 2 that we'll talk about as well. So in some cases, it's easier to just plug in a definition for x and y as their corresponding functions of t. Other times, it's easier to do it via the chain rule. Okay. So for functions of 3 variables, say maybe I have w is a function of x, y, and z, where each one of these is a function of t. So maybe let me write it like this instead, where each one of them is a function of t. Then dw dt is partial w, partial x, dx dt. plus partial w, partial y, dy, dt, plus partial w, partial z, dz, dt. Right, and there's that extra product term that we saw, that we were expecting. So if you get confused about which goes where, or if you just kind of need to remember, so there's 3 variables, so there's 3 separate terms or 3 separate products here, and each product consists of the first term is going to be partial w over the first variable, and then what comes right after it is the first variable, so these always match right here in this diagonal, and then in the lower is the thing that I'm taking my differential. This is dt, right? So dw, and then I have x's, and then I have to follow that up with a dt. Then here's my y's, so my y's across here in the diagonal, as well as my z's across here on this diagonal. So it might be an easy way to kind of remember this form. So let's do another example. Where we're going to find dw dt. Oh, we have a question. Can this be applied to functions with n variables? Of course. So this was 3 variables, but you can keep going. So maybe you had an a here, and then a b, and then a c. You would just keep doing that same logic and tacking on terms, as long as they're all still functions of t. So we're going to find dw dt if w is equal to x times y plus c, and we have that x is cosine t. We have that y is sine of t, and then we have that z is equal to just t. So looking right above here, these are all the terms that we're going to need to figure out what dw dt is equal to. So let's go ahead and calculate those. And they should all be in terms of t at the end. So dw dt is equal to, this is partial w partial x. So for right now, partial w partial x just gives me a y, and then we need a dx dt. So we look at this, and then this just gives us a negative sine of t. Then we need partial w partial y. So we look here for w, and we take our partial. This is just x. And then our dy dt, which is just cosine of t. Next, we have partial w partial z. This just gives us a 1. And then we need dz dt, which is also 1. So now let's go ahead and plug in what y and x are in terms of t. So this is sine of t times negative sine of t plus cosine of t times cosine of t plus, and this is just 1 here. Or we can write this as 1 plus cosine squared t minus sine squared of t. And there we have this cosine squared minus the sine squared again. And we can write that as 1 plus cosine of 2t. So for every extra dimension that you have in your function, you add another grouping here in your chain rule. So it's just a few extra terms that you need to calculate. Okay, so that was all the case one. And case one was talking about when our functions x, y, or our variables x, y, and so on are all functions of the same thing. So I think we're going to start talking about that next time, because I don't want to start it with just about 5 minutes left. So we're going to start next time. We're going to talk about what happens if I have a function, maybe f of x and y, where x and y are also functions of two variables, right? So maybe instead of just t, I have s and t for both of them. How does the chain rule work for something like that? So we're going to stop there. Maybe take about a 5-minute break. Heather is on, and then she'll start her office hours.